All right, so from here, we're going to be working on section 1.3 and 1.4 is my goal for today's lecture class. So, section 1.3 is on vectors. So, let's go ahead and get started on that. All right, so how many of you guys have actually had calculus 3? 1, 2. Okay, we can pick on the rest of them then. All right. So, for the 2 people that I've had in Calc 3, which is where you really get to see vectors applied from a calculus perspective, what do you guys remember about vectors? What makes up a vector? Vectors, pretty much, and this, again, this is section 1.3. Vectors are defined by 2 things. What does a vector have? You got it. Very good. Magnitude and direction. So, typically, you have to have a starting point and an ending point, and you go from the beginning to the ending. So, we can talk about like vectors that we can actually draw. Vectors in R2. R2 is 2-dimension, and with this R, meaning real numbers, that means the vector components, which is the parts in the vector, are coming from the real numbers. So, vectors in R2, and we can talk about the different types, so we can talk about column vectors. Column vectors. You got to give them a name, and traditionally you give them a letter with a little bar over it, and usually it's a little bar with a little arrow at the end of it to remind yourself of your vector, because that's that quote direction. And they got to come from real numbers. So this is a 2-dimensional component, R2. So I have something like 1, 3. That is a column vector. Okay, 1, 3. Let me give you another one. V is going to be the vector -4, 0. And, you know, you can have an arbitrary vector. Let's call them the x vector. Notice the little bar above it. And there'll be the components x1, x2, or maybe xy, whatever you want to, variables you want to write on this stuff. Okay? So, if you draw these guys out, this is your vector. Okay? This one right here is the vector 1, 3, and its positioning is everything. So if I go on a traditional xy plane, first position is going to be the x position, or x1 if you will. The second position is going to be the y, or the x2 position. So if I got 1, 3, you go over on the x position 1, you go over on the y, or the second component 3, 1, 2, 3, and basically you put a dot. It's like an ordered pair. But now, where the vector's coming from is these vectors always originate at the same spot, which is the origin. So here we go, and you connect the 2 dots together. And you go from the origin out to the vector, the dot where the point is at, and you put an arrow. This is what we talk about in terms of a vector. This is your vector. So it has magnitude. What do you mean by magnitude in terms of a vector? It's defined by its length, okay? And you got a direction. This one's going in the first quadrant. It's going kind of northeast looking thing here. And I can go and calculate, if I want mathematics on this thing, I can calculate the angle. And if I need to, I can calculate the magnitude, which is the length of the vector. What would the magnitude be? Well, let's talk about how you plot a vector. I went over x1, up y3. And if you go in that direction, you should be able to see something very geometric, shaped. What is that? It's a triangle. Not just any triangle, it's a right triangle. And the vector is actually the hypotenuse. So I need the length of the hypotenuse, which comes from the Pythagorean theorem. A squared plus b squared equals c squared. 1 squared, 1. 3 squared, 9. 1 plus 9 is 10. So this has a magnitude of the square root of 10. Remember, it's the length of it, so it's the square root of the c part. Does that make sense? And if I want to figure out what this angle is, The angle in standard position is the tangent of the angle is the y component over the x component, or x2 over x1. So this would be the angle of the tangent inverse of 3 over 1. Crappy angle, you can go degrees, you can go radians on it, that's up to you, but it gives you the direction. Does that make sense? Magnitude and direction. So if I look at this vector, what is the vector negative 4, 0? The x component's negative 4, so 1, 2, 3, there's negative 4, 0, put a dot there, and then start at the origin and kind of highlight it and put an arrow at where the vector is at. This is your v vector. This is the v vector, this was the u vector. Does that make sense? Okay? These are column vectors because they're written vertically. You can also talk about row vectors. Vector A would be 0, 1. Vector B, we can make it 1/4, negative 3. Talk about row vectors, okay? And your book will sometimes put a square bracket, sometimes put little pointy brackets. You put some type of bracket around here to notice that it is a, quote, vector and stuff. I like the little pointy brackets because I've taught calculus 3 many times. And this is typically the notation we use in Calc 3. So, but again, if you draw this guy out, where's the vector 0, 1? Well, x is 0, y is 1, so this would be, I'll kind of bold it right here, the arrow, there's your vector A. Does that make sense? Okay? Now, how are vectors equal? Well, components mean everything. So if you got the vector 41, negative 5, and you got the vector negative 5, 41, I know, well, the numbers are the same. Does that make it the same vector? Because the number is the same. The magnitude's going to be the same. Well, nope, not necessarily. They're going to be the same. These guys are not equal to each other. Why not? Well, the components are in different order. So if you actually draw this thing out, 41, negative 5. So x is 41, y is negative 5. Put a dot with a cross at. This would be that vector. So this is the vector, and I'm going to call this guy u, this guy v. So this is the vector u. What about negative 5, 41? That means I had to go over here to negative 5, and then I had to go way up here to 41, put a vector there, and this ends up becoming that particular vector. Does that make sense? This is your vector v. The lengths are the same, but their directions are completely different. So by switching components around, is that going to make it the same vector? No, absolutely not. So these guys are not equal in terms of vectors and stuff. But we got to be able to do math on vectors. So we can sum vectors. So I'll use column vectors because they're the easiest. Negative 1, 3, added to the vector 7, 2. How do you add column vectors? Well, positioning is everything, and you just basically add like terms, you add positions. So it's still a two-dimensional vector. You just add the components. Negative 1 plus 7 for the first component, and 3 plus 2 for the second component. You end up getting 6, 6 as the resultant vector. So this is how you add vector. And you can also do scalar multiples. It would be fine. That would be fine. I should actually look down and look back up at my notes. Thank you. 3 plus 2 is 5. I saw 6 and I wrote down 6 and I saw 6 again. Nope, 3 plus 2 is 5. There we go. So multiple of scalar is this. If I take 2 times the vector 5, negative 3, basically you just scale them and you scale each term. That'll be 2 times 5 for the first component, 2 times negative 3 for the second component. let's just do the math. That'll be what? 10, -6 would be the vector, okay? Now, what exactly is this vector doing here? When you scale it, it's taking the length of it and times 2 is doubling the length. The direction's the same, but the length is going to be twice as far, okay? So from there, we can start doing some algebra. So an example down here would be this. If I let u be the vector, 1, -2, and then I got a second vector, vector v, which is the vector 311. What would 5u minus 8v be equal to? Well, from an algebraic perspective, this would be 5 times the u vector 1, -2, minus 8 times the v vector 311. And then we start doing the scalar multiplication and then the adding of components. So this would be the same thing as 5 times 1 is 5, 5 times -2 is -10. That would be added to -8 times 3 is actually -24. -8 times 11 is -88. And then you add the components. So what would 5 plus a -24 or 5 minus 24 be? -19. What is -10 plus a -88? -98. There is the resultant vector. Does that make sense? Did I lose you guys anywhere? So there's this geometric representation for this particular stuff. So let me show you that. That is this. Again, I mentioned before as I drew these guys out, your geometric description okay? If you got the vector AB, okay? What you got here is you got a ray from the origin, which is the point 0, 0, to the point AB, okay? So if I drew this thing out, declare this to be A, this to be B, right here, here's the origin 0, 0, and you go from the origin to where the dot is at for the AB, this is your geometric representation of the actual vector. So, again, with 2 by 2 and 3 by 3, that's all we can do with this stuff in terms of hand drawing it. The parallelogram or addition. If I take vector u, and I'm just going to draw him over here, I'll declare this guy to be vector u. And I got vector v, and I drew him out here. Here's vector v, and it kind of that's there. Here's vector v. Then, if I wanted to take what exactly is u plus v, what you do is you redraw u, vector u, and at the end of vector u, you add v, and you kind of put yourself a little coordinate axis right there at the end of vector u, and you draw him in there. This right here, vector v, but because of commutativity, u plus v is the same thing as v plus u. So you can sit down here and at the original origin, you can draw yourself a v, vector V, and at the end of vector V, you put a little coordinate axis, and you draw U. It's where all these points, U plus V and V plus U meet up at, it's there, you start at the origin and go to where all the points meet up at down here. That is the resultant of what U plus V is. That is that quote, you create this parallelogram out of this guy. And it's the U plus V and V plus U, and where the last point they all meet up at from the origin, that's the actual vector, okay? So, what would if you got the V vector, what is a negative going to do? Okay? Oh, it's a negative times a component, but what a negative 1 does to a vector is it basically gives you the same vector in the opposite direction. So, over here, if this was vector U, I'm going to draw him in there just like I did before. This is vector U. Where would negative U be? Negative U would be taking this guy right here and making all the components negative, so it's 180 degrees at the same length right here. This would be the negative U vector. Opposite direction, 180 degrees opposite, but the same length. Does that make sense? Which means you are now allowed to do something like this. All right? Just to show you. Again, here is my vector U. Here was my vector V. Just want to use regular positioning here. Here's vector V. What would the vector V minus U be equal to? What would that vector V minus U be? Well, what you're going to do here, V is positive. You're going to have to put in the negative U, which is 180 degrees, same magnitude here. Here is your negative U. And then from there, you basically, it doesn't matter if I start here or go here or here or go here. It's where the two endpoints meet, and then you can, I'm going to just kind of dot this one in here so you guys can see it. I can make a parallelogram out of it, but I'm just having two of them put together. And then V plus negative U, so that would be this vector here. Does that make sense? There is where the vector would be located at. So just getting a feel for, what these particular vectors are going to do for you and stuff. Now, here comes your problem. This is awesome drawing. In my family, my brother got all the art ability. I did not. I am very good with the old school drafting stuff, straight edge, compass, things like that. I was always very good at school with that. But when it comes to freehand art, it's kind of sad. All right, so I am very good with two-dimension stuff. Because of all the Calc 3 stuff I've taught in my life, I am very good at drawing those Calc 3 surfaces of, ellipsoids and hyperboloids and stuff like that. But beyond that, no, it gets kind of tough for me. All right? Now, this is the beauty of linear algebra. This was R2, two-dimensional. R3, drawing an R3 vector. Here is an R3 vector. What's an R3 vector? I'll make him a column vector. Let's say it is 1, 2, 3, because I have no imagination, all right? We'll call him vector U. R3, for you people who haven't had calculus 2 yet, you get your three-dimensional axis. So here is the x-axis coming out of the page. Here is your y-axis, and here is your z-axis. And you put hash marks on these sides. So the x, here's 1, 2, 3. Here's your y, positive 1, 2, 3. Z is 1, 2, 3, 4. And so, these are like number lines. So to the right's positive, 1, 2, 3. Up's positive, 1, 2, 3. Out of the page is positive, 1, 2, 3. Left, down, and back is negative, because there's like three number lines intersecting each other. So again, we start at the origin, 0, 0, 0. This is 1, x is 1, y is 2, z is 3, so you kind of have to put it up there where it would be in space. and then you connect the origin to that guy, and that becomes your three-dimensional vector sticking out from the origin into the first octant of this particular guy, okay? Vectors, yes. Okay, we're math, physics does it differently. Okay, so I drew basically a coordinate axis, and then I put an axis that represents three dimensions, so it's sticking out of the page. So it's kind of diagonal coming out of here, but it's supposed to represent sticking out of the page, so it's three-dimensional. And then you count your hash markings out, to the right and up are the positive ones. On the X, first component, I went 1 unit over. On the Y component, second component, I went 2 over. And then on the third component, Z, I went 3 up. And then I kind of plotted that point sitting in space, and I connected from the origin out to that point. What about vectors in Rn space? So your vector U would be the component, well, you write it as a column component, U1, U2, down to UN. Three-dimension is the best you're going to be able to draw. After 3, N is 45, 207, or whatever. You just have to mathematically draw it like this. And you don't really get a visual representation of that, but you can follow the meaning behind it. Yeah.
Positive into the page or out of the page?
All right, positive is out of the page. Okay, so out of the page, coming this way, okay, is positive. Right is positive and up is positive, okay? That's the mathematical way of doing it. And Y is on the page, Z is up the page. Horizontal on the page is Y, up the page is Z. The physics department wants to do it differently because they're weird over there. And what they do is they put so this is math, much better. Remember what class you're in. This is physics. In the physics department, when they're doing their 3D stuff, they just go with the regular X, Y. So this is 1, 2, 3, right? This is 1, 2, 3. But they make the Z-axis stick out of the page. So this is Z, but still sticking out of the page. This is positive 1, 2, 3 coming out of the page. So they do X, Y, and Z comes out of the page. But Z is always that third dimension, so you think of Z as the height of a three-dimensional object. Heights don't stick out of the page, they go up and down the page. So mathematically, this is much more conducive for that. I mean, it's the same concept, but it's your orientation. Whether you're looking at the pen this way or this way, it's still the same concept, it's just a different view of the same thing. Okay? So this is the way the physics department does it. This is the better way, the math way department does it. All right, so the problem is in dimensions, you can't visualize this type of stuff, okay? But you do have some properties of these guys. You have, like for example, the zero vector. The vector 0. The vector 0. And we would write this the 0 vector, and this would be literally 0, 0, dot, 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 0. And if you draw the 0 vector, what you're talking about here is basically a dot at the origin. Because it's got, because if you think about this being a vector type thing here, it's got no, basically, magnitude to it. So this square root of 0 squared plus 0 squared all the way down is still going to be 0 type thing here. All right? Keep going here. Properties. Say you got some vectors here. Vectors U, V, and W. All elements, these are vectors of Rn. And you've got scalars of C and D. Now, again, discussing this. What's a scalar? A constant. What is a vector? a row vector or a column vector, you've got some kind of a vector with positioning is everything with the little brackets around it, okay? So, number one, properties. U vector plus V vector is the same thing as V vector plus U vector. We would call this commutative, which means it doesn't matter which order you add the two vectors in, it's going to be the exact same thing. Property number two. If I take vector U and add it to vector V and then add that to W, that would be the same thing as taking vector U and then adding that to vector V plus vector W, where you added vector V and W first. What do we call this? Again, in terms of mathematics here, I moved the parentheses. That's called the associativity property. So you have commutativity under addition with vectors. You can do that A plus B, B is B plus A, doesn't matter. And I can move parentheses around, so it doesn't really matter what order I add these vectors up in. It's still going to be the same vector. Property number three deals with that zero vector. If I take vector U plus the zero vector, I'm going to get vector U back again, which would be the same thing as vector 0 plus the U vector. So it doesn't matter which one you add first. You add 0 to any vector, you pretty much get the vector back again. As we mentioned before, what is the negative vector? Well, it does exactly what you want it to do. If I take vector U plus the negative of vector U, which is the opposite direction, same magnitude, pretty much everything cancels, and you'll be left with the 0 vector. Property number 5, if I take a scalar constant C multiplied by vector U plus vector V, that's the same thing as taking constant times vector U plus taking that same constant multiplied by vector V. So in other words, you can distribute a constant through when you're adding or subtracting vectors. Property number 6 says, if I take two constants, C plus D, and then multiply it times a particular vector, that's going to be the same thing as constant C times vector U plus constant D times vector U. So, let me break this down for you in English. You've got two different ways of distributing. I can either take a constant and distribute over two vectors, or I can take a vector and distribute over two constants, and I'm going to end up getting the same result. Does that make sense? And property number 7, if you take one scalar and multiply it times another scalar times vector U, that's the same thing as taking, just multiplying the two scalars C and D together and then multiply it times vector U. Number 8, if you multiply the scalar 1 times vector U, you pretty much get vector U back again. Scaling 1 is not really scaling, you get the exact same vector back again. Now, again, this is where you start getting into the heavy definition stuff. So here we go. You get something called a linear combination of vectors. Again, let's talk about terminology. A linear combination of vectors is this. Yeah, all right, if I have, okay, you're going to get a vector y, which would be equal to C1 times vector 1, plus C2 times vector 2, plus C3 times vector 3, plus dot, 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 plus Cn times vector Vn, okay? Where Ci are going to be, these are constants, also known as scalars, and the Vi's with little bars over them, those are your vectors. And the way you really need to think about these scalars is this. Scalars is basically like your weighting. These are weights. Okay? So you got vector V1, V2, V3, V4, and you can start adding these guys together. You can take a scalar constant times one vector plus another scalar constant times another vector, and this kind of weights the different vectors together, but this is called a linear combination of vectors. Okay? give you an example. Put this page over here. Let's set A1 be a vector, and I'm going to make it 3, -1. I'm going to let A2 be a different vector. I'm going to let it be equal to 2, 5. And then I'm going to call a different vector B, and I'm going to let it be equal to 1, 0. Does there exist scalars C1 and C2 such that C1 times A, 1 vector, plus C2 times A2 vector is actually equal to the B vector? That's the question. Let's look at it real quick. So in other words, if I multiply C1 times the A vector, 3, -1, plus C2 times, this is your A vector here, plus C2 times your A2 vector there, this is A1. The A2 is what? 2, 5? 2, 5. Can you get the B vector out of this guy? 1, 0. You with me so far? We're in the world of vectors, and we're trying to figure out, can I get scalars that I can put in front of these vectors as a linear combination to get a third vector B? Let's rewrite that. Well, if I rewrote this in terms of how you add vectors, you can write this as one big vector. This would be C1 times 3, or 3C1, plus 2 times C2. Okay? The second component would be -C1 plus 5C2. That would have to be equal to 1, 0 vector. Does that make sense? How do you multiply a scalar times a vector? You multiply the scalar times each component within the vector. How do you add vectors? You add the components. This is just a combination thereof. How are two vectors equal to each other? For two vectors to be equal to each other, you end up getting 3C1 plus 2C2. That first component has got to be the first component what it's equal to. That has to be equal to 1. And -C1 plus 5C2 has to be equal to 0. And all of a sudden, you went from playing in the world of vectors to systems of equations again. Now, how would you find the solution for this guy? What would you do based upon what we did at the beginning class here? What kind of matrix? Augmented matrix. You see where we're going with this stuff here. So we're going to do an augmented matrix, which would be 3, 2, augment with 1, -1, 5, augment with 0. Okay? Hey, if I was going to do this particular augmented matrix, and then I'm going to go for the RREF here, all right, I would do this. I would row swap, right? Row 1, swap with row 2. That would give me -1, 5, augment 0, and 3, 2, 1. Then, just because I want to be consistent on this thing, I would do negative row 1, replace row 1 with that one, and that would give me 1, -5, augment 0, 3, 2, 0. Now I'm going to sweep down and go after this guy. So -3 times row 1 plus row 2, replace row 2. That would give me 1, -5, 0, 0. -3 times -5 is 15. 15 plus 2 is 17. And I lost a term here. That's a 1 there. Sorry about that. Carried away. Yeah. Okay, yeah, there's a 1 there. And now 0 times -3 is 0 plus 1 is 1. Then I'm going to make this guy a pivot by multiplying by 1/17 times row 2, replacing row 2 with that. That gives me 1, -5, augment 0, 0, 1, 1/17. And then I got one more move to make. Sweep up and kill him. I'm going to go multiply 5 times row 2, added to row 1, replace row 1. and then you end up getting 0, 1, augment 1/17. Sweeping up, 0 times 5 is 0 plus 1 is 1. 5 times 1 is 5 plus -5 is 0. 5 times 5/17, 5 times 1/17 is 5/17 plus 0 is 5/17. And what do we discover? 3 dots in a triangular fashion means we discover this represents the C1 variable, this represents the C2 variable. So C1 scalar had to be 5/17, and the C2 scalar had to be 1/17. So the answer to the question is, does there exist scalars C1 and C2 such that we can have this equation? The answer is yes. C1 is 5/17 and C2 is 1/17, okay? So, here we go. Put my little paper over here and take a look at this guy here. So you begin to see the importance of that system of equations and solving. We're playing around in the world of algebra here. All right. So, more definitions. Sorry, welcome to section 1.3 and a little bit of 1.4 as we're getting there. Okay? Definition. Okay? Let V1, V2, ... all the way out to VP be a set of vectors in Rn. Rn means each one of them has n components. There are p of these vectors. The first definition that we're going to talk about is the word span. Again, this is terminology. Then the span of the little pointy bracket V1, V2, ... VP vectors is the set of all linear combinations of the vectors, of these vectors VI. Now, what is a set of linear combinations? To be a span, a set of linear combinations is this. A set of linear combinations of a set of vectors, V1, V2, all the way out to VR, let's say, or VP actually, VP of Rn, is a set of vectors of the form C1 times V1 plus C2 times V2 plus ... plus CP times VP for any, key word right there is any, C1, C2, all the way up to CP of real numbers. You can put any scalar in front of these guys, and that becomes the set of linear combinations. So to be in the span of a set of vectors, you are going to be a linear combination. There's going to exist a C1, a C2, ... however CP, however many there are, that I can put in front of these vectors and be equal to the vector that I'm interested in, that B vector. So, back to this problem I just did a few seconds ago. Okay, where was my problem I did a few seconds ago? There it is right here. So if I go back and look at these problems here, this example, you see these two vectors? A1 was the 3, -1 vector, A2 was the 2, 5 vector, and we had this B vector of 1, 0 in terminology. The vector B is part of the linear combination of these two vectors because there exist scalars down here, C1 and C2, right? C1 being 5/17, C2 being 1/17. That made this vector as a linear combination of these two vectors. In other words, the vector 1, 0 is in the span of A1 and A2. Linear combinations and span are very closely connected. For a vector to be in the span, there's going to exist constants that you can plug in front of the vectors, that the vector is a linear combination of those other vectors. So you get to see this kind of double language here with this particular stuff, okay? So, for any vector y that's in the span of a set of vectors vi, we have this. There's going to have some constants. C1 with times vector v1 plus c2 times vector v2 plus ... plus cp times vector vp for some constant c1 through cp elements of real numbers. That's what it means for a vector to be in the span of a set of vectors, okay? There exists a linear combination constants and stuff there. So quickly, before I let you guys go, I did a quick example down here just to show you this one. Same thing as what I just did a few seconds ago, but I made it higher dimension. This is a 3-dimension. So I got A1 is 1, negative 2, 3. A2 is 5, negative 3, negative 13, negative 3. And B is negative 3, 8, 1. Is B, is this vector in the span of these two vectors? So we need to be able to find a C1 and C2 in R that'll make C1 times A1 plus C2 times A2 equal to B. So C1 times your first vector plus C2 times your second vector equals B. And then I write it as a matrix, an augmented matrix, and then my goal is to solve for this guy. Does that make sense? What would you do? Take 2 and sweep down and kill this guy off and kill this guy off. And then again, I will show you quickly, that's exactly mathematically what I did. I swept down and killed those two guys and I get this matrix. And then, wait a minute, then I took this guy to kill this guy off. And notice my reduced echelon form. What did I end up getting? When I haven't quite done there, but I've got it in row echelon form. What do you have? 0, 0, and this is augmented with negative 2. That is inconsistent. What does inconsistent mean? No solutions. What does that mean in terms of this concept? There is no C1 and C2 that you can get this equation, which means B is not in the span of these two guys. Does that make sense? So, there's some homework online that I want you guys to go ahead and start looking at. It is the homework, traditional homework number 1, as well as you should already have your access code to the online homework, and go ahead and start working those. Some of those problems on the online are easy, very quick. Some of them are more complicated. The ones that I put on the traditional are the more complicated show your work type thing. But make sure you read directions. We'll talk more about that next time. See you guys on Thursday.